In this part of the video, we're going to look at a convention that is used by scientists worldwide. Imagine that you do a research at different parts of the world. You want to be able to communicate with the rest of the world in a very similar manner. And that's what led to the development of the international system of units known as Système International d'Unité, short SI units. And the basic units. So the SI basic units are going to be meter for length, kilogram for mass, second for time, and Kelvin for temperature. We are going to discuss temperature in the next chapter. For now, let's focus on the other ones. And this system is not arbitrary. It is based on some standard. For example, the standard of length, the meter, is based on the speed of light. If we were to take light in a vacuum and measure the distance it covers in 1 over that many of a seconds, which this is the speed of light, we'll get the definition of a meter. That means a meter is the same no matter where you at in the world. Unlike that when you have the size of a king's foot sometime in the dark ages, that we still use it until today. That's not the same. The mass, on the other hand, the kilogram, until 2019 was defined as the mass of a block of metal that was kept at 2 different places, but it was changed last year, and now the standard of a mass is defined by taking a fixed numerical value of Planck's constant. This is the value right there, and the units for this is kilogram meter square per second square. If we were to define the meter and the second in terms of the speed of light and a specific atomic transition frequency, we'll be able to calculate kilogram. Way more accurate, way more precise than the alloy that we used before. That alloy was deviating every few years or so, and it had to be calibrated all the time. This one is fixed and never changes anymore. For example, the standard of time is defined by using an atomic clock. So if we look at cesium-133 isotopes, it will undergo that many radioactive events. And if we were to measure these, that is the definition of a second. All right, so it is constant everywhere. We also talked about mass measured in kilograms. In chemistry, we are not going to worry about the difference between mass and weight, but we need to be cognizant of it. We need to realize that what we measure in a laboratory, what we measured on a scale, is actually the weight, and that weight is the mass times gravity. So it's the weight is gravity dependent. If you take a physics class, you need to know the difference between mass and weight. But for chemistry, we're gonna be okay between those differences. So we're gonna use them interchangeably. In addition to these measured values and the units for length, mass, and time, there is a derived unit, and that would be the volume. A volume is a derived unit. In other words, it's formed from other units. For example, if I want to measure the volume of a regularly shaped object like a cube, I would measure the dimensions. And because cube, all the sides are the same, I just cube that measurement. So if the basic SI unit for length is meter, then you would expect the SI unit for volume as a derived unit to be cubic meter. But since we're not going to be working with such large volumes in chemistry, the common unit that we're going to use is cubic centimeter. And I want you to know the difference between a common and the basic. This is the basic unit. This is the one we're going to use a lot, the cubic centimeter. And sometimes we use cubic milliliter. Now let's say I want to measure the distance between the wheels of a car, right? You can measure that in feet. If I want to measure the length of a piece of paper, I'm going to have to measure that in inches. If I want to measure the length of a football field, I'm going to measure that in yards. If I want to measure the distance between LA and San Diego, I'm going to use miles. So you notice that for every type of measurement, whatever it is we're trying to measure, we are using an appropriate unit to measure it. Not only, notice that the examples I just gave you are all have to do with length, but I used different unit to calculate, to measure that length. So I needed an appropriate magnitude of the unit to measure. So it's not appropriate for me to measure the distance between Los Angeles and San Diego using an inch or a yard. It's appropriate to use a mile. So choosing an appropriate unit within the same system is crucial. And this brings us to the what we call the SI prefix multipliers. If I'm measuring something that has a great distance, I'm not going to use something like a meter to measure the distance. I'll use something like megameter. Okay, for example, let's say I'm trying to measure the frequency on a computer processor chip. You measure it in gigahertz, right? So we use gigahertz. So you see that giga, it's a billion hertz. We don't use hertz to measure that. If you're measuring the, for example, the resolution on the camera on your phone, you measure it in megapixel. There's the mega right here. If you're measuring the storage capacity on a PC computer, then you measure it in terabytes, and so on and so forth. So these are called prefix multipliers. Table 2.2 in your textbook is to be memorized. You're gonna need to memorize this. I'm gonna share with you how we're gonna use these in conversions. For now, just an introduction what that is and how you memorize it. Now let me tell you how you read that table. I would like to include right here on this side equivalent to the common unit. Not the basic, but common unit. So for example, if I am looking at the value of 1 picometer, okay, the common unit is meter, 1 picometer is equivalent to 10 to the negative 12 of a meter. Okay, so the way this works, you're gonna put 1 next to each of these, equivalent to whatever common unit is going to be on this side. Okay, so that's the way you're gonna read that table. This table is where students make a lot of mistakes. So I urge you to read it properly, be able to use these prefixes, and always think about it logically. The way this table is written, large units on top and smaller ones at the bottom. So the way, if we were talking about the US customary system, I want you to think of it mile on top and you have inches at the bottom. So you're going to have a lot more inches in a mile, right? And this is where students make mistakes with the exponents. They go positive or negative. Just for 1 second, if you don't understand what I'm saying right here, what you can do is ignore the sign of the exponent completely and just think of it. If I'm going, this is how it goes. If I'm going from large to smaller unit, my exponent is always positive. And if I'm going from a smaller unit, I'm converting from smaller to larger, my exponent is always going to be negative. Smaller to larger, exponent negative. Larger to smaller, exponent is going to be positive. Let me explain what I mean. For example, 1 meter contains 10 to the negative 12 terameter. Okay, so I'm going meter is a small unit, and I'm going to larger one. Therefore, it's going to be negative. On the other hand, 1 terameter contains 10 to the 12 meter. And that's the way you want to read that table. Okay? Notice that when it has the tera right here, that uppercase T, it says 10 to the 12. But notice when I wrote it in terms of going from smaller to larger unit, my exponent was negative. Going from a larger unit to a smaller unit, my exponent is positive. So you can, actually a good exercise is for you to rewrite all of those as two equalities like I just did right here. And if you want, you can check with me. You can send me your paper and I'll look at it and I'll tell you if you got it correctly or not. So how do we do these conversions? We're going to learn a technique, a problem solving in order to convert between these units. Whether we are using within the metric system these prefixes, or we're going between the metric system and the US customary system, it's exactly the same approach. What we do, we are going to read the problem as written and think about it critically. There is no magic bullet here. There is no one way of doing these things. But what I'm going to share with you is a technique that would allow you to develop a strategy to solve word problems. I understand that one of the limitation of teaching a math class and students that take a math class, they really don't learn how to solve word problems. They teach you techniques, how to solve. They give you an equation and say solve the equation. That's not how it works here. There is no specific equation. You just have to be able to read the word problem and be able to develop a technique in order to solve that problem. And we have two types of approaches. One is by using the unit conversion type. We're going to call that dimensional analysis. In other words, I'm going to take an equality and write it as a ratio. So if you take an equality, you write it as a ratio. So let's say I got myself 1 meter equals 100 centimeter. Okay, so it's 100 centimeter. They're equal. So if I write 1 meter over 100 centimeter is the same as writing 100 centimeter over 1 meter, because both of those are equivalent to 1. So in other words, unit conversions is taking an equality and write it as a ratio. We're going to take an equality as such. 1 meter equal 100 centimeter. I can write it as a ratio this way or that way, depending on what I need. Because when I put two things over each other that are equal, it's going to be equivalent to 1. And if I multiply anything I have by 1, it's going to give me the same answer over and over again, but different representation. All right? We'll talk about this in a little bit more. Other way is when you're trying to solve a problem that requires a specific equation. For example, let's say I'm trying to calculate the speed of oxygen molecules in the room. What do I need? I need a formula for that. I need to know that the distance that these particles are going to cover and the time. Then I can take distance over time, I get speed. But for gaseous particles, because they're constantly moving, we use a different formula. All right? So we use a different formula that is dependent on their weight and square root and temperature and all this stuff. But what I'm saying is some problems require specific equations, where the majority of the problems we're going to treat them the same way we treat unit conversions. So I'm going to give you lots of examples on unit conversions, and we're going to go from there. The way you do it is as follows. You start with whatever unit that you have. You take an equality and write it as a ratio by putting the same unit in the denominator with your ratio. This would allow you to cancel the starting unit out, and this will get you a desired unit. For example, let's say I'm trying to convert between the metric system in length to the US customary system in length. We always go to 1 inch equals 2.54 centimeter because it's an exact value. So I can write it as 2.54 centimeter over 1 inch. That's equivalent to 1. 2.54 over 1 inch is equivalent to 1. That quantity, I can multiply it over and over and over again as many times as I want. Or I can write it as 1 inch over 2.54 centimeter. Either way works. Okay, so let's say I have 44.7 centimeter and I would like to convert that to inches. Then I'm going to take 1 inch equals 2.54 centimeter, and I need to write a ratio with that. The ratio I'm going to come up with is not going to be 2.54 centimeter over 1 inch, but it's going to be 1 inch over 2.54 centimeter. The reason I want centimeter in the numerator, in the denominator, because my starting unit is centimeter, and I would like to cancel out the centimeter. So I go centimeter, centimeter, they cancel out, and from that I convert to inches. All right, that's how it works. Every time you have a problem, I would like you to read the problem, gather the information that you have, and based on the information that you were able to extract out of the problem, you should come up with what we call a solution map. The solution map would allow you to figure out which one of these two I need. What am I going? Am I going from centimeter to inches or inches to centimeter? What type of conversion do I need? Am I converting length? Am I converting volume? Am I converting mass? What is it? So you need to figure out, what am I converting? Am I going within the metric system, or am I going between metric and US customary system and back and forth? You need to ask yourself all these questions in order to come up with a solution map. The solution map will be something like this, going from inches to centimeter or going from centimeter to inches. Dependent on which way you're going, you can write the ratios differently. See? Centimeter in the numerator, centimeter in the denominator here. Inches in the denominator on top, inches in the numerator at the bottom. All right? So the process is always going to be identify your starting point, which we call the given information. Then you identify the end point, what you must find. Once you do that, then you can string along a solution map. How do I get from point A to point B using units? That's the way it works. That's the solution map. It's just the diagram that would allow you to go from point A to point B. So you should sort your information, then come up with a strategy. That strategy is what allow you to come up with the solution map. I'm going to share with you a few examples, hopefully can help you understand what I'm trying to tell you here. Once you have a solution map, you'll be able to solve the problem by stringing out units throughout. Then check your answer. Always check your answer. Okay? Check the units and check if the magnitude of your answer make sense. So let's take a look at an example. Convert 7.8 kilometers to miles. So I'm going to ask myself, I'm actually converting a length measurement, and I'm going from the metric system to the US system. Anytime I think of it that way, then I need a relationship between these. So let me write down what I want. I have 7.8 kilometers. That's what's given to me. I need to convert it to miles. I can go to, so the solution map is going to be going from kilometers to miles. And in order to come up with this ratio right here, I'm going to go and look at table 2.3, which gives me the conversion for length. That would be between kilometer and mile. I have meter and inches, meter and yards, foot and centimeter, inch and centimeter. So I can use any one of these and it works. But since we're doing one step right now, let's stick to one step conversion. And that would be this particular relationship going from 1 kilometer to mile, which 1 kilometer has 0.6214 miles. So a kilometer is only 60% of a mile. So when I check my answer, I should get a distance that is less than 7.8 kilometer. That's how I check my answer. So let's set it up. Now that I have my solution map, let's set it up. I start with 7.8 kilometer. I'm going to take this equality right here and write it as a conversion factor. Since I'm starting with kilometer, I need kilometer to be in the denominator, and I'm going to put 0.6214 mile in the numerator. By setting it up like this, I'm going to multiply 7.8 by 0.6214 mile. Kilometer cancel with kilometer, and I'm left with a mile as a unit. And now I end up with 4.84692 miles. I have 4 sig figs in this conversion factor, 2 significant figures in my starting measurement. So I need 2 significant figures in my answer. My units are miles. Check. My value is lower than 7.8, so the magnitude checks, so my answer makes sense, so I can move on. You can practice some more using the following problem at the end of your textbook. For now, I would like you to work on the following. Try to convert 0.825 meter to millimeter. Pause the video, come back and check your answer. So we're given 0.825 meter, and I want to convert it to millimeter. That means I'm converting length within the metric system. So I'm going to use table 2.2. I'm going to take this equality, millimeter to meter. So going from meter to millimeter, I want meter in the denominator and millimeter in the numerator. So this works here. Then let's set it up. 0.825 meter times 1 millimeter over 10 to the negative 3 millimeter. We'll convert it to millimeter, and I get 825 millimeter. 3 sig figs. This one has unlimited number of significant figures. It's an exact, so my answer is 825 millimeters. Since millimeter is a smaller unit than meter, my answer should be way larger than my starting, and it is. And the units are millimeters, so unit and magnitude check. So I'm good there. More practice, so you can do problem 69 to 72. In addition to solving a single step problems, we can actually do a multi-step conversion. So let's say I want to go from centimeter to feet. I can either use the following: foot to centimeter conversion one step, or I can use inch to centimeter. That means I need to convert from foot to inches first. So I'm going to do it in a long way. So we can see that we can do it in a multi-step and you can still get the same exact answer. So let's go from centimeter to inches, then from inches to feet. I'm going to use that same table, 2.3, to come up with these 2 conversion factors. Since I'm going from centimeter to inches, I need inches in the numerator. Then I'm going from inches to foot, I need foot in the numerator. Then all I have to do is set it up. I start with 194 centimeter times 1 inch over 2.54 centimeter times 1 foot over 12 inches will give me the following value, 6.3648. I start with 3 sig figs. This one is exact, this is exact, so my answer should have only 3 significant figures, 6.36 feet. All right, let's look at another example here. A recipe for making creamy pasta sauce calls for 0.75 liter of cream. Your measuring cup measures only in cups. How many cups of cream would you use? 1 quart is 4 cups. So let's sort the information. I'm given 0.75 liter and I'm looking to represent that in cups. So I am using volume in the metric system. This is not the basic unit, this is a common unit, liter. And I'm going to convert it to cups. That means I can use this table right here, and I'm going to go down to volume right here. It says 1 liter. I only have conversion between liter and quarts, so I can go from liter to quart. So I need to look at what I have available to me and use that to construct my solution map. I want to go from liter to quart. Then it's given to us in the problem that 1 quart has 4 cups. Then I can go from quart to cups. So liter to quart, I'm going to take that equality right here, 1 liter to quart. And I'm going to put liter in the denominator, quart in the numerator. This will allow me to go from liter to quart. So I'm going to do 0.75 liter times 1.057 quart over 1 liter. This will give me quart. Then I want to go from quart to cups. So I want quart in the denominator and 4 cups in the numerator. So I multiply by this ratio right here. This will allow me to convert to cups, 3.171 cups. I start with 2 sig figs. This is 4 significant figures. This is exact. So I need 2 sig figs in my answer. Since quart is a little bit larger than a liter and there are 4 cups in a quart, my answer should be larger than 0.75. All right? And it is. The units are correct. Cups. So my units check and the magnitude of my answer check. So I'm good there. More practice, you can look at problems 85 and 86. All right, now your turn. Go ahead and pause the video, solve this one, and come back and check your answer. 1 lap of a running track measures 255 meters. To run 10 kilometers, how many laps should you run? So we're given 10 kilometers and 1 lap equals 255 meters. And I want to figure out how many laps is that. That means I'm going to go from kilometer to meter. Why meter? Because meter will allow me to convert to lap. Kilometer does not. So I convert from kilometer to meter, then from meter to lap. Using this equality, I can go from meter to lap right here. And using table 2.2, I can find out that 1 kilometer is equivalent to 10 to the 3 meters. Set it up. 10 kilometer times 10 to the 3 meters over 1 kilometer. Then I'll multiply that by 1 lap over 255 meters. That will give me the following value. I start with 3 sig figs. These are exact. So I need 3 sig figs in my answer, 39.2 laps. The value, the magnitude checks, and I got the right units. So you guys can do more practice, problem 83 and 84.